we study not invariants because we want to know what we can take for granted that we're seeing in a diagram for a knot, right? In other words, if you draw me a diagram for a knot and then claim that that diagram tells me something about the knot, I don't necessarily have to believe you, right? Because we potentially lose a lot of information when we take a three-dimensional knot and we squish it down into a two-dimensional representation of a diagram using arcs and crossings, right? So if you claim that your diagram is telling me something about the knot that it represents, then that property that you're describing had better be something that doesn't depend on which diagram of that knot that you gave me, right? If you and I have two different diagrams of the same knot, then whatever property you're claiming is a property of the knot, we had better be able to agree upon that property in our two different diagrams. All of the different diagrams for a knot have to tell the same story. And that's how we know that we're talking about a knot invariant. If you and I are talking about a diagram property and every single possible diagram of a given knot will tell the same story with respect to that property, then we call that property a knot invariant. And so the utility of knot invariance is that it gives us a way of telling for sure whether or not two different diagrams represent different knots. If I have a property that definitely is a knot invariant, and so it attaches to the knot and not to the diagrams, and you give me two different diagrams and that property disagrees on these two diagrams, then I must know that those are diagrams of different knots. Because if they were diagrams of the same knot, then all diagrams would have to tell the same story with respect to that property. So every knot invariant is capable of telling different knots apart. If you give me two diagrams of different knots, my invariant will be able to detect that difference every time. Unfortunately, the converse is not always true. It's not always possible for two diagrams which agree to guarantee for me that they are diagrams of the same knot. Because conceivably, right, there might be some other diagram of that knot whose value disagrees with the value that we saw over there. So not every invariant property has the complete invariance that we would have expected, for example, from the tangle fraction of rational tangles. When we were talking about rational tangles, every tangle, it can be represented by a single rational number, and those are actually in one-to-one correspondence with one another. Different tangles have different rational numbers that represent them, and different rational numbers always represent different rational tangles. And so if we understand all the rational numbers, then we understand all the rational tangles, and vice versa, and that is just like the perfect world that we wish that we could live in, right? That's the perfect universe. Unfortunately, complete invariants for knots and links are much, much harder to come by and much, much harder to work with. And so it's our quest over the course of the next week, when we come back a week from today, we're going to get a chance to meet really the only complete invariant that we know of for knots. It's called the fundamental quandle. But that's a really sort of scary, messed up looking, hard to really wrap our minds around algebraic object that we're going to talk about when we come back next week. And so in the meantime, what we want to do is develop a few examples of knot invariants that are a little bit easier to work with to get us used to the idea of what an invariant is, and maybe more importantly, how to test whether or not a given property is or is not actually a knot invariant. So again, the definition of what it means for something to be a knot invariant in the first place. A logical property is called an invariant if any two diagrams, D and D prime, of the same knot will have the same truth value for this logical property. So if, if this is true for one diagram of the knot, then it has to be true for every diagram of that knot. If it's false for one diagram of that knot, it has to be false for every diagram of that knot. That's how we know that that property that we're talking about is a knot invariant. So here's where I want us to get started. We just have a couple of activities to do with invariants for today, so we'll be able to wrap up in time today. Here are three different diagrams, and all three of these diagrams represent the unknot. I think it's pretty easy to see why the first and the third one represent the unknot. And if you were to lay this other one on the table, you could figure out some series of Reidemeister moves that we could use to show that this actually is a diagram of the unknot. So here's what I want your groups to wrestle with, and we'll give you maybe 20 minutes to really do justice to this question. Which of the following four properties is the same for all three of these diagrams? So I give you these four different candidates for knot invariants. The first one is the total number of crossings in a diagram. The second is the difference between the number of overcrossings and the number of undercrossings that we encounter in a complete trip around the diagram. That's like if I start at a certain point on my diagram and just sort of follow it around. In this example, I'm going over at this crossing. And then the next thing that I do is I come back around is I go under. And then I end back where I started. Right? So sort of count the overs and the unders as you trace your fingers through the diagram exactly once. Right? Count the overs, count the unders, and just subtract overs minus unders. Also, the total number of arcs in the diagram. So this diagram of the unknot has a single arc. This diagram over here doesn't have a single arc. It has more than one, right? And then whether the total number of arcs in a diagram is an even number or an odd number. Those are 4 different diagram properties, things that we can tell about a diagram just by looking at the diagram. The question is, are we telling something about the diagram only, or are we telling something about the knot that that diagram represents? And the way we get at that question in this example is just asking, are these properties, each of these 4 properties, the same across all 3 of these diagrams, or are we finding some disagreement? And based on the answers that you give here, figure out which of these 4 properties might be a candidate to be a not invariant. Maybe it's all of them, maybe it's none of them, but doing this exercise gives us some practice with how we might be able to tell. And then we'll develop an algorithm for doing so after we finish this activity. So I gave you 4 different diagram properties and asked you to try and assess which of those diagram properties might actually be a candidate to be a not invariant. In other words, the diagram might be able to tell us a story about the knot and not just about the diagram that we select for it. And so we did this by taking 3 diagrams of the unknot and then asking which of these 4 properties agrees on all 3 of these diagrams and which ones might not agree. So for example, if we just take as a property the total number of crossings in the diagram, as team 2 recognizes here, that property is in fact not shared by all 3 of these diagrams of the unknot, right? This first diagram has 0 crossings, the one in the middle has 3 crossings, the one on the right has 1 crossing, and so the total number of crossings is different for these diagrams, but these are all diagrams of the same knot. Therefore, what can we conclude about the total number of crossings in the diagram? Is that or is that not a not invariant? Remember, in order to...
For just number 1, you're asking?
Yeah, just think about the total number of crossings in the diagram. And
Then
we
it
say
would
that
not,
that's an invariant of knots.
it would not be an invariant.
No, it doesn't work. Because here are 3 diagrams of the same knot whose total number of crossings is not the same for these 3 diagrams, right? So that cannot have been a not invariant. That's absolutely not out of the question, right? Because in order to be a not invariant, it has to be the same for any diagram of a given knot. And that's clearly not the case because all 3 of these represent the same knot, namely the unknot, but they disagree on the total number of crossings that they have. So we can't use the total number of crossings in a diagram to tell us anything about the knot that that diagram represents. On the other hand, number 2, the difference between the total number of over and the total number of under crossings that we see in a complete trip around the diagram. When we do that process, what you noticed, what team 1 notices here, is that when I run around the knot, the difference between the over and the under crossings for all 3 of these diagrams ends up being 0, right? On my first diagram here, I don't have any over or under crossings, so I guess we can say we have 0 of each, and 0 minus 0 is 0. On my second diagram, if I take a shuttle around, starting maybe up here, I'm going to encounter an under, followed by an under, followed by an under. So I kind of have 3 unders in a row, and then I have 3 overs in a row after that before I get back to home. So there's 3 of each. I subtract them. 3 minus 3 is 0. Same thing here. If I do a full trip around the figure 8, I'm going to encounter an overcrossing once and then an undercrossing the second time. So the total number of overs minus the total number of unders is 0 for all 3 of these diagrams. So it seems like maybe that's at least we have seen no evidence that that is not an example of not invariant, right? In order to be absolutely sure that that was a not invariant, we would need to know something a little bit more, and that's what we're going to talk about next. But for now, we can't rule out property number 2 as being a not invariant. Property 3, on the other hand, the total number of arcs in the diagram, that one we can rule out. I just realized that I'm scrolling and you can't see what I'm scrolling here. Property 3, we can rule out the total number of arcs in the diagram as not being a non-invariant because there's a different number of arcs in these diagrams. There's one arc in the diagram on the left. There's only one arc in the diagram on the right. Single unbroken curve can make my figure 8, but there's 3 arcs in this diagram in the middle. So for sure, the total number of arcs cannot be used to tell me anything about the knot. It tells me something about a diagram, but it doesn't tell me something about the knot, because if I change the diagram without changing the knot, I could change the total number of arcs. So we don't like that as a knot invariant. It's not going to work. Whether or not the total number of arcs is even or odd, on the other hand, we don't seem to get any disagreement from these 3 diagrams of the unknot, right? We have an odd number of arcs in this diagram. We have an odd number of arcs in this one and an odd number of arcs in that one. So all 3 of these diagrams for the unknot have an odd number of arcs. So maybe the parity of the arc number tells us something about the knot. Maybe it's a knot invariant. But team 2 observed that we can make a different diagram for the unknot that actually has an even number of arcs. It's this one right here, right? Just take an unknot and introduce 2 crossings to it, either by doing a double twist or by doing a poke. In other words, by doing 2 type 1 moves or a single type 2 move. It looks like in this diagram, they've opted for the former, so they've done 2 twists to it. But if you look at how many arcs this diagram consists of, if I start right here, I follow the first arc back around to there. And then the second arc begins on the other side of this crossing, passes over there, and then ends back here. So this diagram has 2 arcs, which is an even number, and yet it's still a diagram for the unknot, right? So even though these 3 diagrams did not disagree on whether the total number of arcs was even or odd, we can find a different diagram that does disagree with it. And so the parity, the evenness or oddness of the number of arcs in a diagram is also not going to be a knot invariant according to that. So the only candidate that we have left is this difference between the number of overcrossings and the number of undercrossings that we would get in a complete trip around the diagram. So let's see if we can figure out a method for us to tell for sure when something is a knot invariant. It's pretty simple now to rule out something as being a knot invariant. Just find me 2 different diagrams of the unknot where my property disagrees, and then we can throw the whole thing out, right? But telling that something is an invariant is going to require a little bit more of us.